We now turn our attention to section 7.4, which is on the areas of polygons and also circles. From our study of measurement that we did back in chapter 8, we already know that the area of a geometric figure is the measure of the amount of space that's inside of the figure. And when we talk about areas, these are things that are going to be two-dimensional, and so the units are going to be things like square feet or square meters. Let's take a look at the first example. We want to find the area of a rectangular room. And especially as you're kind of reading through and doing a lot of the problems in this geometry section, if you're able to go ahead and diagram them out, a lot of times that can be helpful. In example 1, we have a rectangular kitchen. So I'm going to draw a rectangle here. And we're told that it's 8 feet by 10 feet. So I have 8 feet by 10 feet. And what we're going to do is we're going to tile this with tiles that are 12 inches on a side. So in this floor, we're going to put tiles that are 12 inches by 12 inches. And the question we want to know is, how many tiles is it going to take? In other words, what is the square footage of our kitchen area? And then how many tiles would that take? The area of a rectangle, this will be our first formula in the section, but it's going to be area equals length times width. We have 10 feet times 8 feet, which would give us 80 square feet. So the area of the kitchen is going to be 80 square feet. Now, how many tiles would this take? Well, notice that the tiles were told were 12 inches by 12 inches, but it's equivalent to saying that it's going to be 1 foot by 1 foot, since we know that 12 inches equal to 1 foot. So the area of one of our tiles is going to be 1 times 1, which is 1 square feet. And if we wanted to know how many tiles it would take, well, the answer is it's going to be 80 tiles. We have 80 square feet, and each tile is 1 square feet. So it would take a total of 80 of those tiles in order to perfectly tile this kitchen area. So for a rectangle, so if we have our specialized quadrilateral here, it's going to have a certain length and a certain width. To find the area of a rectangle, it's just length times width. If we happen to have a square, then notice that the length and the width are actually going to be the same. Actually, all of the sides are the same, but it's s times s, which would be s squared. Let's take a look at example 2. We want to find the cost of installing carpet in a room. So we have a room that has the given shape, and we're told that the carpet costs $25 per square yard, and we want to find the total cost of carpeting this room. The first thing that we would want to notice is that this particular kind of room is it's not a simple square or simple rectangle. It's what we call a composite geometric figure, meaning that it's made up of simpler shapes. In order to kind of break the room apart, I can imagine adding either an extra boundary like this, which would break it up into 2 rectangles that have a top and a bottom rectangle. Or another way that maybe I could kind of break this room apart into simpler figures is if I kind of come over here and I drop a line down going vertically. So I could also subdivide the room like this, in which case I'd have like a left rectangle and a right rectangle. The idea is that if I take and find the areas of each of those individual rectangles and add them together, that would give me the total area of the room. I think the way that probably most people would see to split this apart would be maybe using this approach. So that's the way I'll do it. I'll call it R1 and R2. We want to find the area of each of those 2 rectangles. Again, because each one is a rectangle, it's going to be length times width. So A equals L times W. It's also going to be A equals L times W here. If I take a look at the first rectangle, this is going to be rectangle 1. I know this dimension is 10, and this dimension is also 10. So its length times width actually ends up being a square, but it's going to be 10 times 10, which would be 100 square feet. Now we want to find the dimensions for rectangle 2. its dimensions are this by this. Well, we know that the length is 15 feet. That's pretty easy to see because it's already diagrammed. But the other thing that we need to know is we need to know what is its width. It's not labeled on the diagram, but we can figure it out. For example, we know that this whole vertical distance from here to here is 15. We also know that it's what, 10 from here to here. So this remaining length should be 15 minus 10, which is going to be 5. So this width is going to be 5 feet. And so we get 15 times 5, which would give us 75 square feet. We now know the area of rectangle 1. We know the area of rectangle 2. So the total area of our figure should just be add them together. 100 plus 75 would give us 175 square feet. Now that we know the total area, we can start to begin to try to calculate our price. But notice that the price is actually given not in terms of price per square foot, but in terms of price per square yard. So in order to figure this out, we're going to have to first change our square feet into square yards, which is something we did back in our chapter 8 material. To change from square feet into square yards, I want to set up a conversion bridge. We know that 1 square yard is equivalent to 9 square feet. So we end up taking 175, dividing it by 9, which is going to give us 19.4 repeating square yards. I don't want to round this quite yet because we have one more step. We now need to multiply by 25 because it's $25 per square yard. So if I take that 19.4 and I multiply it by $25 per square yard, not sure why I wrote 19.5. We said it was 19.4 with a bar over it. So when I enter it into my calculator, I'm going to put 19.444, as many fours as I can enter. Multiply that by 25, and we would see that to the nearest penny, the total price is going to be $486.11. The next formula we have is going to be that for the area of a parallelogram. In a parallelogram, if you take the distance from one of the vertices, either to the opposite side measured perpendicularly, or perhaps to an extension of a side that goes perpendicularly, that's what we call the height of the parallelogram. The length of the side that the height is drawn to is called the base, and it turns out that the formula for the area of a parallelogram is going to be base times height. So B times H. Let's take a look at this parallelogram. So first thing we want to do is identify what the shape is, and then immediately write down the area formula. It's going to be base times height. I would recommend start by finding the height first. So remember, the height has to be given as a distance that measured from a vertex to an opposite side perpendicularly. So that would be this value right here. This is going to be our height. Okay. So let me call this H. We don't know the value for H. It's not explicitly listed yet, but we can certainly find it because we have a right triangle here. I know that the hypotenuse is 8, and this other leg of the triangle we can figure out because if this one side of the parallelogram is 12, then the other side of the parallelogram must also be 12. 9 of it is from here to here, so if I do 12 take away 9, that tells me that this leg right here would be 3 inches. And Pythagorean Theorem, which says that leg squared plus leg squared equals hypotenuse squared, that will allow us to solve for H. H squared plus 3 squared equals to 8 squared. H squared plus 3 times 3 is 9. 8 times 8 is 64. We're solving an equation. We now need to get the H by itself, so we would subtract 9 from both sides. we get h squared equals 55. And then for the last step, to get h by itself, we need to get rid of a square, which means to do a square root. So we see that the height, h, is the square root of 55, which if we plug that into our calculator, is going to be approximately 7.416 blah, blah, blah. It's irrational, so it's just going to keep on going forever. But that's our height. So it's that 7.416. I'm going to use as many of those digits as I can until I have to round at the end. And the base, which is the side that the height is drawn to. So from this vertex, I'm drawing the height to this side. The length of that whole side we know is 12. So we simply multiply. And to the nearest, if I round it to the nearest tenth, it would actually, it's 88.99, which is going to end up rounding it to 89.0. And because the units were in inches, that means that the area will come out in terms of square inches. So the area of that parallelogram is 89.0 square inches. The next object we're going to look at is going to be the area of a triangle. In a triangle, we have a height as well, which is the distance that's drawn from one vertex that intersects either the opposite side or an extension of the opposite side perpendicularly. That's what we define as the height. The length of the side that the height is drawn to is called the base, and we get the formula for the area of a triangle, which is going to be 1/2 times base times height. So area of a triangle, 1/2 base times height. Let's take a look at this example here. We want to find the area of a triangle. So the moment that I realize it's a triangle, I write down my formula, 1/2 times base times height. The next thing we have to do is kind of read through this diagram to see what's what. So I see that this 5 feet is drawn from this vertex. It's dropped down perpendicularly to intersect an extended side at a right angle. That makes that 5 feet the height. So the height is 5. The side that the height is drawn to is this side. Although it's an extension of the side, it's this particular side, which has a length of 11. That makes that our base. So the area of the triangle is going to be 1/2 times 11 times 5, which if we work it out is going to be 27.5 square feet. So the area of that triangle is 27.5 square feet. We now come to the area of a trapezoid. So if you remember a trapezoid as being that, it's a parallelogram. It's not a parallelogram. It's a quadrilateral where you have exactly one pair of parallel sides. We have a line that measures from a vertex to the opposite side or an extension of that opposite side perpendicularly. The two sides where the non-parallel lines intersect, we have what's called the bases of this trapezoid. So we have a small base and a bigger base, and the area of the trapezoid is 1/2 times the height times the sum of the two bases. Another way that you'll commonly see it written is it's the height times the average of the two bases, is sometimes the way this formula is presented. So if you take a plus b and divide it by 2, that represents the average of the two bases times the height. That gives the formula for the area of a trapezoid. Let's see if we can find the area of this trapezoid. So I recognize the shape, immediately write down the formula, 1/2 times h times a plus b. For this trapezoid, the height, that's the distance from a vertex to the opposite side intersected perpendicularly. That's going to be the 4.5. So 1/2 times 4.5 times the sum of the two bases. Our smaller base here is that number 14, and the larger base would be the one all the way down here, which is 19. If you have a scientific calculator, you can plug this in one shot. If you're using a basic calculator, do order of operations first. You would first take 14 plus 19 and then multiply all the three of those numbers together. Either way you compute it, we should work out to an area of 74.25 square feet. So 74.25 square feet. The next object we're going to come to is going to be the circle. So the definition of a circle is it's the collection of all points that are a fixed distance from a fixed point. The fixed point is called the center, and the fixed distance is called the radius. If you measure the distance going across the circle from end to end that passes through the center, that's referred to as the diameter of the circle. And certainly we can kind of see the relationship that if you had the diameter, that would encompass two values of the radius. So we can see that the diameter is twice the radius, or you can think of the radius as being half of the diameter. The distance, the notion of the distance around the outside of a circle, it's not a polygon because it doesn't have sides. So we give its distance around the outside a special name. It's referred to as the circumference of the circle. And depending upon whether you want to use the diameter or the radius, we have two equivalent formulas for circumference. You can take circumference and multiply it. The circumference is equal to pi times the diameter, or the circumference would be 2 times pi times the radius, where pi is this irrational number. It's an invariant of the circle, and it has a value that's about 3.1415, blah, blah, blah. It's one of those values that never stops, nor does its decimal ever repeat. Let's take a look at this example here. It says a dirt track is set up for amateur auto racing. It consists of a rectangle with half circles on the ends as shown. The track is 300 yards wide and 700 yards from end to end. What is the distance around the track? So we want to find the total distance. If you were to walk around this thing, how far would we travel? This is another great example of what we called our composite geometric figures, because it's not just a simple circle or a certain rectangle, but it's actually a combination of those types of simpler figures. So let's take a look at what we have here. If we kind of draw some extra lines, you can kind of divide the circular end on the left side and the right side of this figure like this to be kind of like circular pieces. We can also figure out exactly the lengths of these linear portions as well. To figure that part out, let's take a look at this. Notice that it's 300 yards all the way across, which means that if I'm looking at like this circular arc, for example, from here to here, that means that this is 300 yards. Or that the radius would be 150 because it's half of that 300. But if I take and draw a radius in this direction, this would also be 150. So it's 150 from this point to the edge, and it's also 150 from this point to the edge. Because I know that the whole thing is 700, I can figure out how much we're going to have here. If I take that 700 and I subtract off the 150 that's here and the 150 that's there, well, 150 plus 150 is 300, and 700 take away 300 will leave us with 400. So the length of either one of these straight line portions of our rink or arena is going to be 400 yards. So for the total distance around the outside, I have these two lengths, each one of which is 400. So if I add the straight line pieces together, we get 800 yards. And now the only other outside portions we need to cover is the distance from here to here, plus the distance from here to here. Each one of those would be like half of a circumference of a circle, But if we put them together, we would actually get a circumference of a full circle that has a radius of 150 yards. Let's go ahead and find the circumference of that circle. Circumference is 2 times pi times r. This is going to be 2 times pi times 150. We can plug this into our calculator. 2 pi times 150. Rounding it to the nearest tenth, we would get 942.5 yards. So that represents the distance around the curvy part from here to here. But then don't forget, we also have to add the 800 yards from our straight line pieces. So we have our 942.5 plus 800 to give us a total distance around the outside of 1,742.5 yards. So for anybody that walks around the outside entirely of that racing rink or wherever it is, they would have covered a distance of exactly 1,742.5 yards. We are also asked to find the area of the rink. And again, that's going to be done by doing a composite geometric figure. If we take that rink and split it apart, what we get is we get these two half circle pieces. So we get like a half circle portion here, a half circle portion there, which when we combine them will give us the area of a full circle whose radius is 150. And we also have what's going to be on the inside part, which is going to be this rectangle. Its width we showed was 400, and its length was 300. So the total area of the rink should be the area of these two figures put together, which we can go ahead and calculate. And I might have scrolled past it, but the area of a circle is pi times radius squared. So the area of the rink is going to be pi times 150 squared for the circular part. So that's going to be pi times 150 to the second power. So on your calculator, you either need to do 150 squared, or you can do 150 times 150, which would give us 70,685.8 square yards, because it's area. And for our rectangle, it's going to be length times width. That's going to be 300 times 400, which should be 120,000 square yards. And then for the total area, we just have to add the two together. So for the total area of our figure, it's going to be the 70,685.8 square yards plus the 120,000 square yards, which should be equal to 190,685.8 square yards, because it's an area. So that would be the total amount of space that is inside of the track. And I really like this last example because it's a good illustration of being able to find not only the distance around the outside, which is what we call the perimeter or circumference if you're dealing with a circle, as opposed to comparing it to the amount of space on the inside, which is meant by the area.